What specific problem does the method presented in your paper aim to solve regarding the understanding of linear representations in supervised learning?
The method presented in the paper aims to address the gap in understanding why supervised learning, particularly through cross-entropy minimization, is effective in recovering interpretable and transferable representations. Specifically, it seeks to extend the identifiability guarantees from weakly self-supervised learning, SSL, to standard supervised learning, demonstrating that models can recover ground truth latent variables up to a linear transformation even in classification tasks. By proposing a cluster-centric data generating process, DGP, and utilizing the diet method, the paper shows that the learned representations are linearly related to the ground truth representations. This theoretical framework provides insights into phenomena such as linear representation hypothesis and neural analogy making, ultimately explaining the success of supervised deep learning across various tasks. Thus, the work offers a unifying theory that connects the effectiveness of supervised classification to the identifiability of latent variables.
Can you describe how the proposed diet method works? Illustrate it step by step, explaining its components and the rationale behind each step.
The diet method operates by solving an instance classification problem, where each training sample is assigned a unique instance label, and data augmentations do not alter this label. First, it employs a composite model, consisting of a backbone that generates 81-dimensional representations and a linear bias-free classification head that maps these representations to a logit vector corresponding to the training dataset size. The core of diet is the cross-entropy loss, which is optimized to ensure that the learned representation captures sufficient information to distinguish between different samples, even within the same class. This is achieved by assigning a unique weight vector to each sample, which aligns with the cluster vectors representing semantic classes, thus ensuring that the learned representations reflect the underlying data distribution modeled as a von Mises-Fisher (VMF) distribution. Ultimately, diet's design allows for the recovery of latent variables and cluster vectors, demonstrating that supervised learning can be viewed as a special case of instance discrimination, where the instance labels are replaced by class labels, leading to linear identifiability of the features.
Could you provide a simple example illustrating the inner workings of the diet method? Walk through the key steps involved with this example.
The diet method operates by solving an instance classification problem, where each training sample has a unique instance label. For example, consider a dataset of images of animals, where each image is labeled with a specific animal type, e.g. cat, dog, bird. The diet architecture consists of a backbone that generates 81-dimensional representations of these images, and a linear classification head that maps these representations to a logit vector corresponding to the unique instance labels. During training, the model uses the cross-entropy loss to optimize the representation such that it can accurately distinguish between different animal images, effectively learning to align the learned representations with the corresponding cluster vectors of each animal class. This process ensures that the learned representations capture the underlying structure of the data, allowing for the recovery of latent variables that are linearly related to the ground truth representations, as demonstrated in the theoretical framework of the method.
What theoretical or practical benefits does the diet method offer over existing methods in the realm of representation learning and supervised classification?
The diet method offers significant theoretical benefits by providing identifiability guarantees for latent variables in both self-supervised and supervised learning contexts. Specifically, it extends the identifiability framework to standard cross-entropy-based supervised classification, demonstrating that models can recover ground truth latent variables up to a linear transformation. This is crucial as it connects the success of supervised learning to the underlying data generating process, DGP, in a cluster-centric manner, which is not typically addressed by existing methods. Practically, diet's architecture, which separates the encoder and classification head, allows for better alignment of learned representations with class vectors, enhancing the interpretability and transferability of features. Empirical results corroborate these theoretical insights, showing that DIET can effectively recover latent variables across various datasets, including synthetic and real-world scenarios like ImageNet-X.
How did you validate the effectiveness of your proposed method? Discuss the experimental setup, datasets used, and the metrics for performance evaluation.
To validate the effectiveness of our proposed DIET method, we conducted experiments on both synthetic and real-world datasets, specifically the DisLib disentanglement benchmark and ImageNet-X. In the synthetic setting, we generated data samples based on our cluster-centric data generating process, DGP, using a von Mises-Fisher (VMF) distribution around cluster centroids, and evaluated the recovery of ground truth latent variables through the R-squared score. For the DisLib benchmark, we trained a 3-layer MLP and a CNN, ResNet-18, to assess the Pearson correlation between predicted and actual latent variables, focusing on object attributes like position and scale. In the real-world scenario with ImageNet-X, we utilized pre-trained models, ResNet-50 and VitB16, and measured performance using accuracy, correlation, and F1 score against a random baseline. Our results consistently demonstrated that representations learned via supervised learning allowed for linear decoding of latent variables, supporting our theoretical claims.
What specific results did you achieve with the DIET method in your experiments, and how do they support your theoretical claims regarding linear identifiability?
In our experiments using the DIET method, we achieved high R-squared scores for the recovery of cluster vectors and ground truth latent variables, demonstrating that the learned representations effectively captured the underlying data structure. Specifically, we observed R-squared scores close to 1, indicating that even with many clusters and samples, the DIET method successfully identified latent variables up to orthogonal linear transformations. Additionally, our results showed that the performance improved when using semantic class labels instead of instance indices, suggesting that even coarser classification tasks can yield linearly identifiable representations. These empirical findings corroborate our theoretical claims, particularly the identifiability guarantees established in Theorem 1, which assert that cross-entropy-based classification tasks can invert the data generating process and recover latent variables linearly. Overall, our experiments validate the effectiveness of the DIET method in achieving linear identifiability, supporting the broader implications for deep learning models trained with cross-entropy loss.